The other next problem on the formative assessment was to graph a polynomial, this polynomial right here. It says sketch the graph of this polynomial. And it is already in factored form for us, thankfully. It might be, if it was given to us in standard form, that might be quite challenging to figure out what all those factors are. But I also provided a pretty detailed list of what I was looking for in this problem and the things that we want to include in a quality sketch. We want to include our roots labeled with their x coordinates. Okay, let me just start there. Because this polynomial is already factored, I can just figure out the roots by inspection. Remember, the roots are the values of x that cause this polynomial to equal 0. What numbers do I put in for x to get 0 out of this function? And you can see that if x is 4, or if x is -3, or if x is 1, then those are the three values that cause this function to equal 0. Let me just place those on my graph. Here's a -3 right there. I'll make a point. Here is a +1 right there. Make a point. And then finally, we have a root at 4, x equal to +4. So there, I've done the very first step. I've labeled my roots with their x coordinates. Okay? I'm going to come back to this y-intercept business. It does want us to label the y-intercept with its y-coordinate. I'm not going to put the y-intercept on my graph yet, but I will just calculate it. And I could do that by just substituting 0 in for x. That's how you find the y-intercept of any function. You just put 0 in for x, figure out what you get for y, because no matter where you are on that y-axis, the value of x is equal to 0. So I'll just maybe go right here and say f of 0 is equal to 1/2 times -4 times 3 to the 2nd power times -1 to the 3rd power. And I've just substituted 0 in for x into my function, and I can just kind of quickly go through this. This becomes 9. This will stay -1. So this together becomes a -9 times a -4. That is +36. And then I want half of that. So that gives me a +18. So I've just done a little calculation to figure out my y-intercept. Okay, and I'm going to use that information later. It says, draw a smooth curve through all important points and on the correct side of the x-axis. So there's a lot of ways to draw a nice smooth curve through these 3 roots. But I need to make sure that I'm on either the positive or the negative side of that x-axis along the appropriate intervals. And so one of the ways that we determined this before was by actually picking a number on, say, like down on this interval, like -4 or -5 or -6, and then plugging it into the original formula and determining whether or not the result was positive and thus above the x-axis or negative below the x-axis. I'm going to approach this a little differently this time. I'm going to use the multiplicity of these roots and that y-intercept that I just calculated to figure out what happens on these different intervals. Well, I know that my y-intercept is positive. It's +18. So this along this interval, my graph has got to be above the y-axis because I have a result that's positive. So let me imagine what happens down here. Notice that this root right here came from this factor, which has a multiplicity of 2. I know that when things have a multiplicity of 2, they're going to go back the way they came. So I expect the graph to be positive over here also. The other two, this root has a multiplicity of 3, which is odd. And that means that the graph is going to cross from the positive region into the negative region here. And then, again, the root that the factor that gives us the root of 4 also has an odd multiplicity, a multiplicity of 1. And so I expect that the graph is going to cross the axis there also. So if you tested some points to figure out whether your graph is positive or negative, that's fine. But there's other ways to use the multiplicity and maybe just one point, like your y-intercept, to figure that out. I'm now, before I draw this smooth curve, I want to just make sure that I use an accurate sketch of the behavior near the roots. Here's what I mean by that. I know that this root, -3, comes from a factor that is squared. And so I'm going to get some like parabolic-like behavior right here. So I just sketch that in. And then I know that at 1, the multiplicity is 3. It's a cubic. And I'm coming from the positive to the negative. It's not just going to go straight through that root. It's going to level off, and it's going to inflect like this. Okay? So I get behavior like this around the root that is cubed. And then the root that just is a single linear factor to the power of 1, it's just going to come right through like that. So now I can connect all of these like this. I'm going to come down, I'm going to go up, and then come down and meet up with my cubic. And then I'm just going to dip down and come back up like this. And there, that's a great looking graph. Okay, I've got that root behavior, that cube, the root that's cubed has a certain behavior right here. Maybe the last thing I'll do with this line is just add the arrows on the end to describe and express that it goes on forever. As x goes to -infinity, my graph continues to go up. As x goes to +infinity, my graph continues to go up, just like that. And let me just run through my list real quick. I got my roots labeled with their x coordinates right there. My y-intercept, I've calculated it. Let me just label it with its y coordinate. Here it is. Notice I put the point on there after I draw my curve. It's just a little easier to draw my curve without having to aim for a point that I drew already. So I label that. I got my smooth curve through all the important points and on the correct side of the axis. It only dips below the axis, the x-axis here between 1 and 4. And I took careful attention to draw the right behavior near the roots. And so my graph is done. It's beautiful. I love it. Now, I'm going to make a note describing the end behavior using appropriate notation. And this is just a little bit of memory, but also expressing what we understand happens at the ends of this function. And I'm just going to first make a statement about as x approaches +infinity, my function, f of x, approaches +infinity. And that is just an expression of what happens here on this side of the graph. I want to do the same thing for the negative side of the graph. As x approaches -infinity, f of x also approaches +infinity. Okay? So that is a nice, clear statement. No equal signs, right? Remember, we don't equal infinity, we approach infinity, and we approach -infinity. So there's a complete solution for that problem.